Let's start. I think so. Now it's already lecture six out of 7. So final lecture is going to be in 2 weeks. And today we're going to talk about probability distributions and a geometric perspective on statistics and the processing of those objects. So first, quick recap, exactly the same slides as 2 weeks ago. Where are we going? Okay. The whole spirit of the class is that we are trying to mitigate the curse of dimensionality by putting more or less domain-specific knowledge into our programs. Okay, because we've seen that naive vanilla statistical programs require an exponential number of samples with respect to the dimension. So if you have more than 10 columns, it's impossible to pick an off-the-shelf statistical toolbox and apply it on your data and expect, let's say, competitive performance. So one way or another, you need to fight against this by lowering the dimension of the problem. So the first way that we've seen in lecture 2 is just to use expert knowledge, discuss with domain experts and get access to high quality features. And we know that, okay, if you have high features that are good enough, then probably standard baselines from the 80s, 90s are going to work, okay, and are going to be done, and you can move on to another problem. Okay. Otherwise, we've seen that sometimes even the experts do not really know what to do with all their features. Then you have some heuristics that help us to work and try to get out of this. So usually we can hope to use relevant families of functions, either let's say mathematical families of functions like kernels, or domain-specific architectures like convolutional pyramids for image processing that today we call convolutional neural networks. In other fields, maybe we have access mostly to relevant neighborhood structures. And then we say that we work with graphs. Again, that was the lectures about graphs and geometric deep learning. And in all of this scientific program, our main challenge is that we want to go from local implementations. All of our programs, they deal with edges, small kernels, small convolutions, but we want to take a step back and get a global understanding of what happens when you scale to millions of samples. And this is a non-trivial part of doing geometry in machine learning. And at least my job, as an academic, is to try to be inspired by the program that people actually use, like things that visibly make sense in real life scenarios for real life data. Try to understand what is happening, like why are people converging towards some kind of computational architectures. Try to abstract them, and in return, produce guidelines and insights for practitioners. And part of it is trying to make good lectures, because most of you are going to be in the industry one day, and I think that if you have a kind of abstract, deeper outlook on the programs that you are writing, probably it's going to be easier for you to be more creative and also to debug things more easily. So now, in the second half of the class, we've tried to introduce a continuous vocabulary for data sciences. Okay? The idea here is that if you have 1 million or 10 millions of samples, probably it's more efficient to think about them as a continuum than as a big set of independent discrete objects. At some point, if you zoom out enough, things start to become continuous, and the whole vocabulary of calculus, continuum analysis, is here to help you. Maybe it's a bit more challenging from a technical perspective, but it's really there to bring you more insights. So 2 weeks ago, we talked about Riemannian metrics, and basically the idea was to see what happens when you try to go from discrete graphs to continuous spaces. Okay, so we spent quite a lot of time talking about the Poincaré disk, because it's one of the, I think, most interesting toy examples, okay, of what can happen when you distort locally the Euclidean metric. Okay, and we saw that out of nowhere by introducing just a field of temperatures, we're able to create a completely different geometry, that is more suited to representing trees than representing grids, essentially. Then we discussed a little bit of real-life Riemannian geometry, how we work with local metrics, and how we try at least to define geodesic path. Now today, instead of going from discrete to continuous spaces, we're going to see what happens, basically the mathematical framework that's relevant when you go from a discrete sample, like a histogram, to something which is highly densely sampled, so basically continuous distribution. Try to understand histograms and densities in a common unified frame that mathematicians call measure theory. Yeah. So we are going to start the lecture by trying to say why we care about probability distributions. I mean, I assume that you kind of know that it's going to be important because we know that machine learning is related to statistics is related to probability, but probability distributions come up in many surprising settings, like in shape analysis. Then I'm going to present to you the classical geometries that we can define on spaces of probability distributions. So mostly everything that's related to entropy, so information geometry. Then everything that's related to Euclidean spaces like Hilbert spaces or kernels. And then everything that's related to Wasserstein metrics, so optimal transport. Okay, and basically, once I will have presented to you like those three major families of geometries, okay, we're going to try to build up some intuitions by making a real lab session, on gradient descent with those kind of loss functions, trying to fit one population of samples to another by minimizing a distance. And we are going to see that depending on the distance that you choose to quantify discrepancies between probability distributions, you get very different dynamics. Okay, so I mean, for everything that I'm going to talk about today, the main reference, like the accessible reference, is the third chapter of my PhD thesis, which is called Geometric Data Analysis Beyond Convolutions, that you can download on my website and which is filled with references to actual research papers. Like we're really, the lecture is more or less going to follow the plan of this chapter, that I filled with illustrations, etc. So I think it's a good gateway to the topic for MVA students. So, but first, what is a probability distribution? Maybe the simplest definition is to say that a probability distribution alpha, okay, I'm always going to use Greek letters for those objects, is just a collection of weights, AI, at locations xi. Okay, and this covers already quite a few objects that you may have manipulated so far, in your studies. So first, clearly, it describes histograms and density maps. Okay, histogram basically is what you get when you have a fixed set of locations. So basically different elements in a set, and to which you ascribe different weights, alpha, AI. So when you work with a histogram, usually you do not explicitly recall the locations xi every time you describe the histograms. You only keep in memory those weights, AI. And maybe, if those locations correspond to points in a 2D plane, then your collection of weights can be understood as an image, but an image with only positive values, okay, that should be understood as mass, as densities more than intensities. So, for instance, if you do segmentation, I know in a class in computer vision, then the segmentation method essentially turns an image into a collection of density maps that correspond to different objects. And so directly you recover histograms. Then a second setting in which you see probability distributions appear is whenever in statistics you consider a sample, a discrete sample. So a collection of points in a feature space, or equivalently a data set, okay, where every row is a point and every column is a feature. So here, when you consider a discrete sample, implicitly you assume that the weights are all equal to each other. So let's say that they are equal to 1 over n, if I have n points, okay, so that the total sum is equal to 1. But at different locations xi that correspond to my features. Finally, okay, maybe instead of fixing the locations or fixing the weights, you can work with probability distributions where both parameters are free. And essentially, you recover a weighted point cloud, either in dimension 2, 3, or more. Okay, a weighted point cloud is just encoded as a collection of variable weights AI at variable locations xi. So those weights, have different meanings. We're going to see what they can represent. Maybe they represent local surface areas. Maybe they represent the local importance of the sample. So for instance, in statistics, we call those weights importance weights, okay? When you do importance sampling and all that. So from a mathematical perspective, like, the standard mathematical notation to talk about those objects is to say that alpha is a discrete sum of weighted direct masses. Okay, so here, I write that alpha is equal to the sum for I that goes from 1 to n of AI delta xi. Okay, and delta xi, essentially it represents a probability distribution which is always equal to xi. So a punctual mass. Then when I multiply it by AI, I say, okay, it only has a weight AI. And then when I sum them, I say that I consider basically the average distributions of those xi's. So first remark is that, the sum implicitly, it's commutative, so it's invariant to the labelings of the xi's. And this is the main difference between working with probability distributions and working with point clouds. Okay, when you work with an annotated point cloud or with vectors, you assume that the ordering of your coordinates has a meaning. Whereas if I decide to understand a point cloud as a discrete sum, then implicitly I'm going to restrict myself to operations that are fully invariant to reorderings of the points xi. Okay, so I assume that you can imagine that, for instance, for 3D shape processing, it's relevant because usually we get 3D point cloud, but the actual ordering of the points has no meaning. Okay, so whenever we want to work with 3D point cloud up to permutations, it's often very productive, very efficient to understand that what we are actually doing is we are working with a discrete sample understood as a probability distribution. Okay, so that's for discrete sums. And maybe if you already took lectures on analysis, those discrete sums, they're a bit equivalent to Riemann sums. Okay, basically to pointwise integrals. And basically what you know from lectures on integration or measure theory is that when the number of samples n goes to infinity, you get limit objects that are essentially continuous densities. Okay, continuous densities, alpha, that you represent with those continuous sums that we call integral. And so now the weights are more like density functions times a reference measure. So maybe the Lebesgue measure for Gaussian distributions. Okay, so this is more like background. Today we are not going to be very rigorous, okay, about this discrete and continuous framework because either you already taken a lecture on measure theory or you haven't. Okay, it's not something that we can introduce in 3 hours. But okay, just to tell you that probability distributions encompass all of this. Now today we're going to focus on probability distribution. So we're going to assume that the weights are all non-negative and that they sum up to 1. Okay, like we normalize our distribution. So I assume this mostly for the sake of simplicity, okay, because I do not want to deal with negative weights or measures that do not sum up to 1 in an introductory lecture. But nearly everything that I'm going to tell you today can be generalized, okay, to the more general setting of arbitrary measures, random measures. It's a bit of a disclaimer that we're trying to keep things simple today to focus on the geometry. not on the technicalities. Now, today's focus is going to be on quantifying distances between those objects, okay? Not on quantifying distances between points, but on defining distances between probability distributions. So, this project has two main characteristics. The first is that we must try to handle both discrete and continuous distributions. Okay, everything that we say today should be well defined or be generalized easily, both on discrete samples like point clouds, histograms, and continuous distributions like Gaussian or exponential distributions. The second is that we're going to see that there is no canonical universal standard distance on the space of probability distributions. Actually, there's always going to be a choice that we have to make on what kind of properties do we want to enforce. So I'm not going to present to you the distance on the space of probability measures. I'm going to present you a collection of distances on probability distributions that all have their priors, that all encode a different prior on what it means to be far away. Okay, so just to show you that it's necessarily a non-trivial problem, is that let's consider those three probability distributions. Okay, you have the red one, the green density, and the blue density. Okay, all of them defined on the real line with an area under the curve that is equal to 1. So they all describe probability distributions. And then you have to decide, okay, if the red curve, I call it alpha, do I want it to be closer to the blue one? Because the red curve and the blue curve both have the same mean value, around here. Or do I want the red curve alpha to be closer to the green curve gamma, because both curves have the same support? The answer to this question is very much going to depend on the context. Okay, and so it's important, for me to show you that different formulas like the relative entropy, the cross entropy, or the Wasserstein distance, basically they encode a prior on they come with a ready-made answer to this question, and your job, as a machine learning researcher or as a data scientist, is to pick the distance on distributions that actually reflect the priors that you want to put into your algorithm. Okay. For instance, if you are too restrictive on the supports, you may very well get very strange artifacts, okay, in your program if you don't know what you're doing. Today is mostly about letting you understand basically this toolbox that is available to you. So, okay, now that we have understood that this is what we want to do today, I'm going to show you 5 types of applications that motivate all of this research, okay, for you to understand that there are many different good reasons to want to study probability distributions and to want to do geometry with probability distributions. The first one, in statistics, is what we call one sample or two sample testing. So the idea here is that, okay, in one sample test, I assume that I'm given a discrete observation alpha, so a histogram or a point cloud, and a continuous model beta. In two sample testing, I assume that I'm just given two discrete samples, alpha and beta. And the question that I want to answer is, do these two samples come from the same distribution, or does the discrete sample alpha comes from the distribution beta? It's a natural answer. Basically, you get two data sets, maybe two populations of patients from two different hospitals, and you want to answer the question like, is it realistic to say that they both describe the same kind of population, or are they really different from each other? And so, for this, in statistics, we like to be very explicit about the null hypothesis. So here, we try to design tests where the null hypothesis is that alpha and beta come from the same distribution. And then, assuming that we have defined a good distance between probability distribution alpha and beta, we are going to reject the null hypothesis if we observe that the distance between alpha and beta is too large. And obviously, depending on the definition that we choose for the distance between alpha and beta, we are going to make different types of errors, like first type, second type errors on different types of data samples. Okay. So that's, this is the type of definition that you would find on Wikipedia. Maybe I can tell you, why is it actually useful in real life? And, something that people do in my research team, Eka at INRIA, is, yes?
From the same distribution if one is continuous and the other one is
like, is it possible to say that they come from the same distribution? Yes. Yes. So here, basically the idea is that beta typically is going to be your continuous model, your assumption. So let's say a Gaussian distribution. And then alpha is going to be a point cloud. You're going to get maybe 2,000 samples. And what you're going to yes. Yes. So in one sample test, your model typically is continuous, your sample is discrete, and you want to say, is it likely that my sample comes from this distribution? And in two sample tests, it's more like you have two discrete samples, and you say, is it likely that those two samples came from the same continuous distribution gamma? That's the idea. So it's excellent, to ask questions. It's much better than just me speaking alone for 2 hours. Okay. So in my team, there are several people, who are experts in the design of clinical trials, to get approval for drugs, like the COVID vaccines or whatever. Okay. And what you've probably heard about is that whenever you have a drug, you need to design a trial that's going to demonstrate that the treatment is meaningful, like actually increases the life expectancy or whatever. And so you know that we're going to, basically given 2,000 patients, we're going to split this population into a set of patients who are going to get the treatment, here like in red, and a set of patients who are going to get a placebo, or who are going to get the same treatment as everyone else in the hospital. And we call that the control group. And obviously you understand that if we make the split not evenly, we are not going to make very good science. Okay, like for instance, if you put men on one side and women on the other, if you give the drug to all men and you give placebo to all women, well, we're never going to know if the differences in outcomes are actually caused by the drugs, or if they just come from the fact that at the start you did not take similar distributions, similar subpopulations. And so it's very important whenever you try to design those studies to say, okay, what I have here is I have 10 patients. And for those 10 patients, I know quite a few things. I know quite a lot of important covariates, like features, like the sex, the age, maybe their health habits, how dynamic they are, etc. So basically my population is like a point cloud in dimension 5, 10, 100. And what we would like to do is to define a partition of this point cloud into a red treatment group and a blue control group, such that those two point clouds are kind of indistinguishable from each other from a statistical perspective. And so ideally, we'd like to create those partitions such that a standard statistical test will not reject the hypothesis that they come from the same distribution. So that's very standard. And maybe something that is coming up more and more, is that in real life, each patient, okay, in a clinical trial is extremely expensive. That's what I told you in lecture 4. I think on average, the statistics is that one patient in a typical drug trial costs like $40,000. And in some surgery applications, it's more like $1 million per patient. So, I mean, if you're a pharmaceutical company or if you're just society, you would like to minimize the number of patients that are needed, okay, in any given clinical trial. And so, whenever you see those standard design studies, maybe you feel that we're a bit wasteful because immediately we throw away 50% of our population by just giving them the same treatment as everyone else in the hospital. And so a question that is coming up more and more is to say, maybe we could give the drug to all the patients in our that we actively recruit for our study and compare them to the general population in the hospitals. So the context in which we are is that instead of considering just 10 patients, it's more that we want to recruit 5 patients. We only want to pay those $40,000 for 5 patients and compare them against the general population of millions of people who already get the standard treatment. But obviously, if you do that, it's dangerous because maybe the general population is not at all the same as the population of people that you actively recruited for your clinical trial. And so now the problem that we have is that we want to pick 5 patients in the general population such that this kind of synthetic control group will be indistinguishable from our population of patients that actually receive our new tested drug. Yes.
But if you have only 5 patients, how do you know it's representative of any distribution? Because they're probably just from one pulse.
Yes. No, in real life, it's never 5. Okay, I'm just saying 5 because it's I just put 5 dots here.
I mean, like, how big a sample size do you need to be sure that it's representative of any sort of distribution?
Yes. Yeah, so I mean, that's a big question of making clinical trials. And basically, most of research in this field is about designing tests such that you can have guarantees on this. So basically, you try to isolate patients for whom you can show that you can expect that the treatment is going to be effective. Okay, because for instance, if you only have 10 patients, but if you know that in the general population, they're all going to die in 6 months, and given this drug, they survive for 3 years, then it's very convincing. Basically, you can be you say, okay, I really have a miracle drug, at least for this subpopulation. So this is a type of test that we would like to have. A test where a priori you can select patients that are going to respond well to the treatment, select them in the clinical trial, give them the drug and get miracle results. Okay, and the thing that in real life today, like in oncology, for cancer research, it's not at all what happens. Basically, my understanding, I'm not an expert in that, is that most drugs for cancer treatments essentially work on like 10% of the patients and have no effect on the other 90%. And so what happens is that basically when we recruit patients to hope to find to have at least a population of 100 patients who are going to respond well, we have to pick a few thousand people, and so it's extremely costly. And so now the pharmaceutical company, those clinical trials are a massive part of their budget. Today, they are becoming more and more interested in making maybe smaller claims. Instead of saying that on average, their drug extends the life of people by 6 months, they prefer to say, we have a criterion that allows us to select people who are going to be good responders. And for those good responders, we can expect an increase in life expectancy of 3 years. Okay, and maybe it looks like a smaller claim, but first, it's more interesting for oncologists. Like it's more interesting for the doctors because they know that that drugs work this way. Like they work on some people and on other people they don't do anything at all. And most importantly, for the pharmaceutical company, it's way cheaper to put the second type of claim than the first one because you only have to test on fewer patients. Okay, and so those ideas, it's kind of recent. I don't know how widespread they actually are in the pharmaceutical, in real life pharmaceutical companies, but there's a lot of research going on in this field. And so, for instance, that among those tech companies around Paris that work on AI in healthcare, one of the biggest one is called Okin, and it's typically what they want to do. Okay, it's this kind of business model. they try to sell to pharmaceutical companies software that are going to help them to select good responders to their drugs. Okay. So.
When we try to make the both groups similar, how can we be confident that we've measured everything that's relevant to make sure we've...
Yes, no. So I mean, it's complicated. Yeah, and I do not come from this field. Personally, I'm someone who really come from 3D shape analysis, these kind of things. So it's an environment that I've just been discovering, for about a year and getting more and more familiar with this. My understanding is that, in statistics, statistics is not so much about being super rigorous as being about, trying to design good rules of thumb to prevent, to try to avoid massive mistakes. So it's more that you say, okay, if I have enough covariates that seem relevant, then hopefully I haven't made that big of a mistake. I mean, real life statistics, I think when you're a mathematician or geometer by trade, you think in terms of model. That's what we're embedded in. I think statistics as a science is much more about data. All the notations are about data. Instead of having a model that you apply on data, you have data on which you apply a model. And the thing is that, okay, when you do real statistics, you cannot change the data because it doesn't suit your model. It's more like you have data, it's very complicated. So you try to build up domain expertise, and then you just want to pick a good tool in your toolbox that kind of works, and it's very empirical. And so, it's also an important thing is that in healthcare, consensus is very important. It's something that maybe I didn't realize before coming from mathematics. In mathematics, we say that something is true when we have a proof. Sorry, in healthcare, in those fields, there is no mathematical proof, and there will never be. And nothing is ever going to be set in stone. Okay, so it's more that if a method has been published in good journals, has been given the green light from the big scientific societies in the US, in Germany, in the UK, in France, then maybe people say, yeah, maybe we're just going to do the same thing. So it's very slow to make those things evolve. My understanding, because consensus is so important, basically, if you try to change a consensus, then it becomes a highly political question. And the idea is that if you change the consensus in a direction which suits everyone, less work for doctors, less money, fewer costs for pharmaceutical companies, convenient for the state, then probably you can hope to have a change in consensus. But if you try to change a consensus in a way that damages the interests of one of those actors, for instance, if you try to change the recommendations in a way that you lower the rate of prescription of some drugs, then pharmaceutical companies are going to fight super hard against it. Okay, and that's real life. And maybe you can say, I don't want to have any dealing with this. I want to stay in proof. I'm just saying, it's normal. In any field that has real life impact, there's going to be politics involved. It's part of the game. Okay, and maybe do not feel too attached. So everything we tell you here about AI in healthcare, I don't know how many AI methods developed over the last decade have actually been deployed, on the PACS here. If segmentation algorithms have already been put in clinical use in some hospitals, it would already be a miracle. So it's very slow, but the thing is that once it's there, and it actually changes the life of millions of people. So it's a trade-off. It's not at all the same thing as what you have maybe in some other areas of AI, where just you have an algorithm and bam, 6 months later you have an app, it's deployed everywhere. It's much slower, but it's also much more impactful. So it's trade. Okay. So that was it for the first motivation to design distances between probability distribution. The second one, super important, is that you should realize that classification, it's just regression in a space of probability distributions. And classification is what happens when you replace your least square error with a loss function defined in the space of probability distributions. So to see this, let me consider like a super simple classification problem where I have two input features, like x, y coordinates, and three classes, 1, 2, 3. If you want to solve this problem using linear regression, like the standard thing for regression, what are you going to do? Well, first, we are going to encode our class labels as integer numbers. Okay, so we're going to say that first class, like the red points correspond to label 1, second class corresponds to label 2, and the green class corresponds to label 3. Then somehow we are going to design a model, like a linear model for linear regression, that takes as input a vector of dimension 2, xy coordinates, and predicts a score at every location x. And then, to train the model, we are going to minimize an objective, to minimize a loss function, which is going to be, let's say, the least squared error. So the average value over all my samples x, so here n is equal to 15, 3 times 5, of the squared error between L of x, so the integer number 1, 2, 3, and my prediction, S of x. So, I mean, that's what you would do, if you took your classification problem and applied a standard regression algorithm. And as you can tell, or if you've taken any class on data science, it's a terrible idea to do that. Okay, it's very, very bad. And why is that so? Well, the first problem immediately is that this method is not invariant to the ordering of the labels. Okay, because 1, 2, and 3, the set 1, 2, 3, understood as points on the real line, has a structure where 2 is in between 1 and 3. So when you decide that the blue class is going to correspond to label 2, implicitly you're saying that the blue class sits in between the red and the green class. And so, for instance, your linear model that predicts a score, if you display its decision rule, it's going to look like this. You're going to have a linear function, and in this region, below a certain threshold, it's going to be closer to 1. Like here, I'm just displaying the set of points x such that S of x is smaller than 1.5. Then there's going to be a kind of band in feature space where the label is between 1.5 and 2.5. And then above, here, the predicted label is going to be larger than 2.5, and so it corresponds more to class 3. And obviously, you see that if I had changed the labeling of the classes, I would have retrieved very different bands. Okay? And so, my model clearly doesn't generalize well. Like this point, the model thinks that it's class 2, whereas it's more like in between class 1 and 3, etc. Okay, so this is why, at least in machine learning 101 lectures, we make a sharp distinction between regression and classification. Essentially, understanding a class label as a number, except in some cases, it's a terrible idea. So what do we do instead? Well, the equivalent to linear regression for classification is called logistic regression. And the idea of logistic regression is that instead of understanding our class labels as numbers in the set 1, 2, 3, we understand them as confidence scores or probability distributions on the set 1, 2, 3. So for instance, it's a one-hot encoding of the class label. And so here, for instance, for those 5 points, I say that I have observed the probability distribution 1, 0, 0. A vector with non-negative values that sums up to 1. here, okay, the second class, I say that I have observed 0, 1, 0. And for the third class, I say that I have observed 0, 0, 1. Okay, so basically I have embedded my labels in a space, basically in a space of 3 uples of positive numbers that has the right symmetries. Essentially, with this encoding, with this embedding, the blue class does not sit in between the red and the green class anymore. They all have the same role, like the X, Y, and Z axes in 3D space all play equivalent role. Okay, so that's the core idea. And now, well, how are we going to design a model that predicts probability distributions instead of predicting a number? So the way we do it with logistic regression is that we try to predict a vector of scores, S1 of X, S2 of X, S3 of X, that kind of scores the likelihood of belonging to class 1, 2, and 3. Okay, so at every location, we have 3 numbers. And in order to turn it into a probability distribution, we use a softmax function. So a softmax function is, just takes as input S1 of X, S2 of X, S3 of X, applies pointwise the exponential, and normalize it so that it sums up to 1. Okay, so the properties of this softmax function is that you give it any vector, and it produces a vector that has the same shape, but filled with non-negative values, and that sums up to 1. Okay, and the good thing about the exponential is that it's fairly easy using an exponential to express probability distribution that are very close to being saturated, like very close to 1, 0, 0. Okay, because with the exponential, for instance, if S1 of X is like much larger than S2 of X and S3 of X, like if the gap between S1 of X and S2 and S3 is like 10, then by applying the exponential, you completely crush S2 and S3, and so you're going to recover something that really looks like the perfect probability distribution that you want. Okay, so that's a logistic model. So at every point X, we have defined a parametric way of computing a probability distribution alpha of X, and then logistic regression just corresponds to what happens when you minimize the relative entropy, okay, that we're going to define after the break. So when you do logistic regression, you minimize by gradient descent on the parameters of your score network, of your score model, the average value of the relative entropy, so Kullback-Leibler divergence, between the observed label, so delta of X, which is 1, 0, 0, or 0, 1, 0, or 0, 1, 0, 1, and our model, so alpha of X. Okay, and this method has built-in invariance to the ordering of the labels. And so the kind of decision rule that we get looks like this. Okay, and it's much more satisfying, as a baseline. So that's massive motivation to try, because whenever you do deep learning, usually basically you create a big model that predicts scores, and then your loss function, it's always more or less a cross entropy, okay, between your predicted vector of labels and your delta of X. So implicitly, you are always using the relative entropy. So it's good to try to understand what is the relative entropy and maybe understand that you could use something else. So application 3 is motivation 3 is generative modeling. So this, it's something that's super trendy, in the web or in newspapers. So I assume that you've already heard about it. All those softwares, all the software that generate good-looking images. Okay. So what are they? Well, essentially, they are programs that take as input a large data set of typically natural images. Okay, because generative modeling, you can hope to apply to other fields, but by far the most important application is just natural images. It's the field in which it's most relevant. So in generative modeling, you have these huge data sets of millions of natural images, and you say, I have a big data set. But as you know, it's not so large actually, because the space of images is super high dimensional. So dimension typically 1 million, and so exponential of 1 million is much larger than the size of your data set. So it's a challenge to try to understand the shape of the manifold of natural images in this very high dimensional space, given what is at the end of the day a very sparse sampling of the manifold. Okay, even if you consider all the images that are available online, it's a very sparse sampling of the full space of natural images embedded in the space of all images. So what can you try to do? Okay, so here, in those two, you have two major ways of working, and in those two images, okay, my big data set, like my ImageNet of natural images, it's the blue point cloud. Okay, so a first method, which is what generative adversarial networks do, or variational autoencoders do, is that you try to train a network to generate good-looking samples. And the way you train your network is that, okay, at every iteration, you pick a random variable, so basically you pick some random node, and you generate a sample of images. Like here I had like 8 real images. I generate 8 synthetic images in red. And then at every iteration, you have your sample of synthetic fake images. You have a sample of real images. And then you compute a loss function. You compute a distance between those two samples of images. You compute the gradient of this loss function. And this tells you how you should improve your generation. And basically, you hope to train your network in such a way that after convergence, the point cloud of synthetic images essentially becomes indistinguishable from the sample of real images. Okay, so all those GANs and VAEs, under the hood, or actually quite explicitly in the paper, they rely on the definition of those loss functions between samples of natural images. Okay? So another method, which is what people call diffusion or score-based models, is that we try to train networks to estimate a gradient of the distance to the support of a reference data sample. So the image that you can have in mind is that we have our data sets, our huge collection of natural images. That is, okay, this very sparsely sampled surface, hypersurface in the space of natural images. And now we kind of consider intuitively the distance to this data set in the full space, in the full high dimensional space of natural images. And what we would like to do, so here I display in 2D. Obviously in 2D it's completely different to what you have in dimension 1 million, but that's the image. You consider, okay, just a distance to this data set. And you say, okay, what would be cool is if I could compute this distance efficiently, and even more interestingly, if I could compute its gradient. Because, if you have a set, like a manifold, if you have its distance, and more importantly, if you have access to a vector field that is minus the gradient of the distance function, then at every location of the space of images, you have a direction in which you can go that's going to take you closer to the space of good-looking images. Okay? And so we're going to discuss this at the very end of the lecture. Today, at least for natural images, people are actually able to design networks that correspond to this green vector field. So essentially, given an image, they can tell you, okay, given any image, they say, okay, if I were you and if I wanted to get something that is more good-looking, I would change a little bit the pixel values in this direction. And then all those generated images that you've seen online over the last 3 months, basically they are generated by creating something that doesn't really look good, like by putting patches, or drawing a sketch, and then iteratively, after a few steps, being projected on the space of natural images. Okay, and so this geometric intuition of I have a manifold in the space of probability distributions, and what I'm interested in is like this field of distance to the support of my data set, is really what is behind all this literature. That's one, let's say, inspiring application. Now, application 4, which is the one that I'm actually interested in, or that initially drove me towards geometry and space of probability distributions, is shape registration. Okay, because the problem we have when dealing with shapes is that we're given curves, we're given surfaces, we're given segmentation masks, and we'd like to fit them onto each other. It's the most basic pre-processing that you can do. Okay, given a reference mesh, can you fit it onto a real medical image? But it's surprisingly challenging. Like, it's really not an easy problem. It's very non-convex, etc. So, and the basic property that we'd like to enforce is that our algorithms should be invariant to the discretization, to the sampling of our shapes. If we design an algorithm that gives completely different results when we change the triangulation of a mesh, we can change our job. Okay, it's a very important property to guarantee. And a way of guaranteeing that our shape analysis programs are fully invariant to resamplings is to encode our shapes as probability distributions. So what do I mean by that? Well, consider a curve, a collection of segments, a discrete curve. Then this collection of segments, you can turn it into a probability distribution where every weighted direct mass corresponds to a segment. And so at least the most simple thing you can do is to put a direct mass at the center of your segment with a weight that is proportional to the length of the segment. Okay, and this way, for instance, if you take one big segment and cut it in two halves, you're going to replace one big direct mass by two small direct masses that are around. And from a probabilistic perspective, it's nearly the same object. Okay, so I mean, it's kind of continuous encoding from the space of shapes to the space of probability distributions. Then you can do the same thing for triangles. You can turn your mesh into a collection of direct masses where every direct mass is located at the center of a triangle with a weight that is proportional to the area. And if you have a segmentation masks, well, basically you already have a histogram of probability densities. So, it's a very appealing way of designing robust algorithms in this field. And just to be clear, here in those pictures, I only work with the basic X, Y, Z coordinates of the points, but in real life, you would like embed your directs in a high dimensional space of features, where at the very least, for instance, for triangles, you keep track of the orientation of the triangles, you keep track of the curvature, these kind of things, and maybe you use deep learning features. But basically, you keep in mind this nice probabilistic structure. Essentially, it's equivalent to understanding a shape as the uniform distribution on its surface from mathematical. And even the kind of pipeline that I showed to you 2 lectures ago, the thing about lung registration, kind of explicitly in the paper, it is about minimizing a distance between the deformable model alpha, the source lung, and the target beta. And the loss function is defined using measure theory, explicitly on probability distribution. So that's application 4. And motivation 5 is like doing meta-analysis on histograms and distributions. Okay, the thing is that if you have access to a cheap, to an affordable distance between histograms and probability distribution, then you're able to make a group level analysis. You can start to understand your histograms as points in the space of histograms, and then do everything you can do on vector space in space of probability distribution. So it's relevant maybe if we try to compare different hospitals with each other, for instance. And in imaging sciences, because it's the MVA, it's extremely relevant whenever you talk about texture, because texture it's something that is it's a statistical notion. So here these are pictures that are taken from this paper, that I showed you in the lecture about graphs, which was about curvature. I showed you that you could define 3D shape textures as minimizers of an integral of some polynomials of the curvatures. A very simple ways of defining curvature. And in this paper, you have another idea, which is that if you have a surface or a homogeneous surface, something that has a homogeneous texture, you can identify its texture. Like a good descriptor of the texture is to look at the probability distribution of curvatures. So what do I mean by that? Basically, I identify this 3D mesh with this diagram where every point corresponds to a triangle on the surface. And essentially at every triangle, okay, I assume that all my triangles have the same area here. At every triangle, I compute the two main curvatures, the two principal curvatures, kappa 1, kappa 2. And then I put any triangle in this diagram at coordinates kappa 1, kappa 2. So kappa 1 is always larger than kappa 2. So for instance, just to be clear, here, this surface, if you look at any given point, it looks that kappa 2 is always equal to minus kappa 1. Basically at every location, it looks like a horse saddle. And so this is what we see in this diagram. Okay, basically, the coordinate kappa 2, so y, is always equal to minus kappa 1. So this shape texture is identified with a distribution here along this diagonal of the space of diagram. Okay, and then you have varying values of kappa 1 and kappa 2. You have kappa 1 and kappa 2 are fixed, but they can take different values along this axis. Alternatively, here, it's a shape texture where you have more like tubular shapes. I mean, most of the points locally look like cylinders. The neighborhoods of most points locally looks like a cylinder. So if you take a point at random, chances are that kappa 1 is positive and kappa 2 is equal to 0. And this is what we see here. Okay, like this shape texture is characterized by this histogram value, where kappa 1 can range between 0 and 40, but kappa 2 stays bounded in a given region. Okay, and so this, it's something I show it to you because I find it very cool in 3D, but you have the same ideas in 2D. Okay, if you look papers on texture analysis for images, texture synthesis, you have the same kind of ideas that appear. And then what's very nice is that thanks to modern research in the field, it's possible to visualize a population of such histograms. So here, this is a UMAP representation of a population of 1,000 textures that has been generated by first, for these 1,000 textures, computing a diagram, and then computing a full distance, a full matrix, like a 1,000 by 1,000 matrix of distances between those histograms. And here, it was the Wasserstein distance that is induced by optimal transport. Okay. We're going to see at the end of the lecture. And so it's possible because as of 2022, computing 1 million Wasserstein distances is very cheap. It wasn't 10 years ago, but now it's very easy. And the good thing is that when you do that, you recover a plot that looks interesting. Like it looks like we have captured something about the space of 3D shape textures. Because, okay, maybe it's a bit small for you, but for instance, here you have bubbles. Here you have very small bubbles. And then, in this region, you have things that look like surfaces, like sheets. And then basically most textures in this population that was generated at random correspond to tubes with varying densities. So here, kind of low density tubes, and here very high density tubes. So it's really a kind of analysis that was not possible 10 years ago, But now that we have made a lot of progress on understanding distances between histograms and scaling up their computations, it is becoming possible. So I mean, it's a bit like a toy example, but hopefully someday we're going to be able to make those meta-analyses between hospitals. So that would be very nice. So, okay, what we've seen here is that there are many different good reasons to study probability distributions. In pharmacology, standard machine learning, generative modeling, shape analysis, texture analysis, anything. And in all those different fields, we know, depending on the application, we may choose a different encoding for our distributions. In the first slide, I showed you that maybe we can use a histogram, maybe we can use a discrete sample, maybe we can use a weighted point cloud. And usually, depending on the representation that you choose, you make explicit some of the parameters of your distribution, and you keep others implicit. So for instance, if you work with histograms, usually your weights are explicit. These are the objects that you store in memory as arrays, but the locations are implicit. Okay, yeah, we know that this pixel is close to this one, but we never actually store the coordinates of all the points. Likewise, when you work with a discrete sample, usually you do not store the implicit weights, except if you have very good reason to do so. So for instance, me, I'm doing shape analysis. My triangles have different areas, so I very much keep track of the areas of my triangles as weights. Okay, but in typical like generative modeling, you wouldn't bother doing that. So those different encodings mean that when you look at the algorithm in research papers, they seem very different to each other. Like you see that people use the same words. They talk about kernels, they talk about optimal transport, but they implement things that look very different. And so here I want to stress that if you want to make insightful research in those areas, you must really try to understand that different implementations, like different programs, can correspond to the same operation, to the same mathematical operation. Okay, and I think that this is where having a good mathematical background is really helpful, because if you have a good math background, you are kind of used to this idea that a function, you can represent it, as a sum, as a limit of piecewise constant function, as a limit of piecewise affine function. You can represent it in the Fourier basis. I mean, a mathematical education trains you to having different outlooks on the same objects. And so especially at the MBA, I think you should really use this skill that you have, that has been given to you by your training, because it's something that, in my experience, is very hard to grasp for people who went only through a typical computer science curriculum. Because when you train mostly with algorithms, etc., like with discrete algorithms, when you spend all of your studies studying networks or compression algorithms, and not spending that much time looking at continuous mathematics, understanding those shifts in representation can be a bit hard. To tell you, I think it's one of your strengths. So try to use it. And so a first example is the convolution. Okay, so here, and I mean convolution, you can really encode it and understand it in at least 3 different ways that are all equivalent to each other, even though they correspond to very different code. So here I consider very simple probability distributions. So 3 times the same probability distribution, but encoded in a different way. So here, so basically it's a distribution where I have 3 modes, 1, 2, and 3. This mode, the largest one, this second mode, and this third mode, where you have very little weight. So distribution with 3 modes on the Euclidean plane. And if I encode it as a histogram, it's going to look like this. Okay, I have 3 locations where I have mass, 0 elsewhere. As a discrete sample, it looks like this, like lately just a cloud of 1,000 points, and the information about weights is encoded in the fact that here I have more points than I have here and there. And finally, if I want to encode it as a weighted point cloud, then I have 3 pairs of coordinates, x, y, x1, y1, x2, y2, x3, y3, with weights that are essentially that correspond to the values that were in my histogram. So this is the same object. And what does it mean to convolve this distribution with a Gaussian? Well, you can implement this idea in 3 different ways. If you have encoded your measure as a density map, then making a convolution with a Gaussian kernel, well, you're going to implement it by using a convolution kernel in PyTorch. Okay, right. You're going to take your density map, define a filter that that essentially has value that are filled with exponential of minus x squared plus x plus y squared. Apply your convolution kernel that's going to compute tons of local weighted averages, and you're going to end up with this new image, a new function. A convolution takes as input a distribution, a function, and outputs a function. That's one way, and this is why convolution kernel in PyTorch is called convolution kernel. But then if you had more like a sample, the way to implement a convolution is to use additive noise. Okay, like the main reason why we study convolutions is that this is what corresponds to additive noise. And adding noise to random variables definitely looks like something that is important. Okay, so here, this is a new random sample that I generated by picking points at random in this discrete data set and adding a new, basically a random variable wi, where wi follows, a standard normal distribution in the plane whose density exactly corresponds, to the density that I use here for this grid. Okay, so here you see, visually you see that it's the same thing, but if you look at the program, it doesn't look the same at all. Okay, and finally, maybe something that is most important in 3D geometry, but also for diffusion models. Like this is exactly the idea that is behind diffusion models. Well, if I have a set of 3 locations, if I know where my 3 modes are, then adding, making a convolution with a Gaussian corresponds to considering a Gaussian mixture model. And I can compute the likelihood of this Gaussian mixture model, which is actually the likelihood of this random variable. And then if I look at the function L of x, which is a log of the sum over I, so 1, 2, 3, there are 3 terms in this sum of the weights AI time a Gaussian. Okay, I have forgotten the 1 divided by square root of 2 pi. Okay, let's forget about that. I have forgotten the normalization factor. Okay, so you have this function that is just a function that you can evaluate at any given point in the plane. And if you display it, it really looks like a soft distance function to or square distance function to the support of my measure. And essentially, this comes from the fact that when you take the log of the sum of exponential, you're really computing a maximum, like a soft maximum. And computing a maximum of minus distances, it kind of corresponds to computing the minimal distances, the minimal distance from x to the xi. And this is why the picture looks like this. Okay, and so this is useful both for diffusion models, but in 3D graphics, it's called mutables, and it's a very standard rendering algorithm. If you type mutable, you're going to find 3D graphics telling you how to use this representation of a convolution in Blender, to define cool objects. So, I mean, it's totally real and relevant. Okay, and so this is something that I think is really important for you, okay, going forward, to try to understand that those 3 objects that are all very important all correspond to the same idea. And if you want to be efficient in your research, just like changes of variables are key to make nice proofs, maybe changes of representation are key to designing interesting and scalable algorithms. So that was the point about implementations. And before the break, I would like to make a point also about notations, okay? Because probability distributions have been studied in many different fields for over a century. And so in different communities, people have different interests, and so they choose different notations to talk about probability distributions. They pick notations that highlight what is interesting to them, what is important. So maybe when you have a probability distribution, the most important operation that you can make is the integration of your probability distribution against a test function f. So how do we write this operation? So here I say that alpha, it's a weighted sum of direct masses. So it's a sum for I that goes from 1 to n of ai delta xi. And I consider f, just a continuous function on the sample space where the x live. And then to define the integral of f with respect to alpha, I have at least 4 different notations. The first one is the one that you would find in engineering or programming papers. Just write it as a sum. Okay, you write sum for I that goes from 1 to n of ai f of xi. Basically, the idea is that the Dirac mass delta xi corresponds to an evaluation of f. Okay, it's good because when you see that, it's very clear how you're going to implement it. Now, another notation is the one that is used in your lectures on measure theory and integration theory. It's the one where you have replaced the discrete sum by an integral of f d alpha of x. And basically, this notation highlights the fact that if the number of samples goes to infinity, we are going to get an object that has the same behavior as a Lebesgue measure. Basically, we use the same notations for discrete and continuous measures. Then you have a third notation, which is the one that we use in functional analysis. And functional analysis, the key insight is that, functions are vectors in a space of infinite dimension. And vector, it's a bit like a column vector. And the key insight, if you take a lecture in functional analysis, is that measures are just transposes of functions. They are the row vectors that corresponds to functions. Okay, if functions are columns, measures are rows. Okay, and so the most important things that you can do when you have a row and a column vector is to take their dot product. And so in functional analysis, we just said that the integration is a dot product between alpha and f. So it's a very compact notation. And finally, in probability theory, okay, we like to talk about expectations. Okay, and so we write that the integral is the expectation of f of x, where x is a random variable of low alpha. All of those notations really, they just highlight different things and they correspond to a different prior on what is interesting and what is not interesting. Here you highlight the implementation. Here you highlight the link between discrete and continuous sums. Here you highlight this kind of geometric understanding of making dot products between measures and functions. And here you highlight the statistical nature, or you remember that all of this is very random. Now that's cool, but I think that if you want to study spaces of probability distributions, if you want to define geometries, clearly this notation is better. And why? That because it highlights the fact that this quantity is linear with respect to both distributions and functions. When you have this notation, you clearly see that alpha divided by 2 plus beta divided by 2 times f, like the integral of f with respect to this average measure, is just the average of the integral of f with respect to alpha and the integral of f with respect to beta. Just like the integral of f plus g against alpha is the integral of f against alpha plus g against alpha. And so that's clear notation that allows you to consider combinations of distributions. And for instance, it's something that is extremely hard to write if you use the probabilistic notations. Because when you look at this notation, it's not clear at all that the expectation of f of x when x follows 1/2 of alpha plus 1/2 of beta is going to be 1/2 of the expectation of f with respect to alpha plus 1/2 of the expectation of f with respect to beta. So I would like to stress that, basically the last decade in machine learning on the statistical side has been about kind of discovering the literature in geometry, applying it in statistics, and making new statistical statements on classical distances. And you can say, why did statisticians wait until 2010, 2012 to start doing this? I think that a big part of it is that because the notations that statisticians and experts in probability theory are used to really do not lend themselves to having this geometric understanding of the space of measures. For instance, if you type Gaussian processes in Wikipedia, everything is explained using those notations. I think it's extremely cumbersome. Like, I do not understand anything at the Wikipedia description of Gaussian processes, whereas I could make you a lecture about this using those notations. It would be crystal clear. Like, basically, you would really understand that it's just Gaussian distributions in a space of infinite dimension. So, I mean, those notations play a big role, just like the software library that we use play a big role in what people work on. And I mean, a very positive evolution, I think, in the statistical literature over the last decade is that statisticians have grown used to those other notations, those other perspectives, and have brought very interesting ideas, because basically they are asking completely new questions on those standard geometric objects. Okay, so we've seen quite a lot of motivation from many different directions to study distances between distributions. And so since the subject has been actively studied for at least 70 years, around computer science, but actually since the very beginning of statistics, like Fisher and those kind of guys in the early 20th century, there are many distances between distributions that have been defined. Many distances have been defined between probability distributions, and now, in the next hour, I want to show you, the archetypal major distances between distributions that you are necessarily going to encounter over the next few years, and try to allow you to understand what kind of archetypal priors they represent. So first, we have to realize that whenever we define a distance between histograms or densities, we have to make two main choices, answer two main questions. So first, the archetypal thing that we have in mind is, let's look at classification, image classification, so the high-dimensional equivalent of the logistic regression example that we saw earlier. So we have an image, clearly a lion, and the ground truth label is a histogram over my 4 classes, that associates a weight of 1 to the class lion and a weight of 0 to the classes tiger, chicken, and taxi. Now, what's going to happen most of the time is that during training, our neural network is going to make different predictions. Like maybe one prediction that's going to come up is, no, I don't think it's a lion. I'm fairly confident that this is a tiger. Maybe it's a chicken, and clearly it's not a taxi. And prediction 2 is, I think it's a taxi. Let's say 60% chance, and otherwise, I don't know. Like I toss a coin between a lion, tiger, and chicken. And now the question that we have to ask ourselves, is that we want to define interesting loss functions, because ultimately the link between our model and our data set is always going to be the gradient of this loss function. So if the gradient is not informative, we're going nowhere. So we have massive interest in defining loss functions that generate interesting gradients. And so we have to ask ourselves the question, like, is it better to make prediction 1 or prediction 2? Arguably, personally, if I was trying to train a child, I would say that prediction 1 is better than prediction 2, right? Because a tiger, it's nearly the same thing as a lion. Whereas I would be very, very, very worried if my child was 60% confident that this was a taxi. Okay. But on the other hand, prediction 1 gives a weight of 0 to the class lion. So like this distribution has no overlap with the ground truth distribution. Whereas this one, prediction 2, at least he gave himself some room for doubt. So, immediately you understand that if you want to favor prediction 1 over prediction 2, then probably we should try to leverage the distance, x minus y on the ground space of labels. Somehow use the fact that tiger and lion, it's nearly the same thing, whereas taxi is very clearly far away. And it's not something, for instance, that you're going to get with the cross entropy, because in your definition of the cross entropy, you do not care at all about what about the meaning of the labels. So that's one thing. One main criterion to pick a loss function over another is, do we want to leverage this distance on the space of labels? And second, how harshly should we penalize errors on the estimation of the support? On one side, I could say that, yeah, prediction 1, it's fine. Tiger is nearly close to a lion, but in real life settings, maybe in hospitals, a model that is 100% sure confident that this drug is completely fine, and give it to the patient, it's going to work okay, and actually the patient dies because of the drug, big trouble. Okay, so it's also a question, arguably, the fact that this model is less confident when it is clearly wrong is arguably a good feature that we would like to promote during training. So, it's really a choice that is domain-specific, application-specific. So with all of this in mind, maybe the simplest distance that I can use between probability distributions is the total variation distance. So let's assume, today that my space is discrete. I have a finite set of labels, x1, xk. And now the space of probability distributions on this set of labels is a set of vectors of dimension k, with k coordinates, with positive coordinates. So I work like in a cone of the full vector space of vectors, and with a constraint, which is that the sum of all the weights should be equal to 1. So geometrically, I am defining the intersection of a cone with a hyperplane. So it's called the simplex of dimension k minus 1. And here I am displaying it to you, with just 3 classes. So lion, tiger, chicken. So I have 3 different 3 weights, a of x1, a of x2, a of x3 that I have to choose. All coordinates should be positive. The weight should sum up to 1. It defines this triangle. So the dimension of the space of probability distributions is kind of k minus 1, the number of labels minus 1, because you have one scalar linear constraint. And on this space, it seems idiomatic to use the L1 Manhattan distance. Since the space of probability distributions is defined using the sum of values, maybe what I should do is to define the distance between alpha and beta as the sum over all labels of the absolute difference between the weights a of xi and the weight b of xi. So geometrically, if I have my 4 classes, lion, tiger, chicken, taxi, and I have a first histogram like the red one, a second histogram, the blue one, the total variation just corresponds to taking the sum of all the lengths of the differences, between the weights and summing them all together, and it gives me a score, like it gives me a distance. So it's good because it's very simple, but what are the first properties, the first intuition that we should have about this distance? Well, first thing is that the total variation distance is at most going to be equal to 2. Okay, that's a triangular inequality. If I take this sum, a of xi minus b of xi, it's always smaller than a of xi plus b of xi. And so this sum is going to be smaller than the sum of all the a of xi's plus the sum of all the b of xi's. Each of these sum is equal to 1. So at most, my TV total variation is going to be equal to 2. And actually, it's simple to identify the cases where we saturate the constraint, where we saturate this value. It happens when the two histograms have disjoint support. Basically, if the two distributions never allocate mass on the same points. So good. Now, as far as those properties are concerned, my two main criteria, this formula, it pays zero attention to the structure of the space of label. I did not use the fact that tigers and lions are closer between each other than they are to chicken. So it pays no attention to the ground metric. And also quite interestingly, it pays no attention to unlikely events. Basically, the importance of a given label in my classification error is directly proportional to how likely they are to appear. Okay. So basically, unlikely events are just rounding errors as far as the total variation is concerned. So it can be fine, but I would argue that in most real-life scenarios, it's not such a good idea, to have this behavior, especially in the medical setting, because unlikely events are exceptional events, and usually exceptional events are kind of important. Like basically in a hospital, maybe the patient has a strange condition. You do not want to pay zero attention to it. Maybe you don't want to emphasize it too much, but you should take it into account. And here it's completely negligible. So, with this perspective that maybe using an L1 metric is not the best idea in the world, maybe we want to have a more probabilistic mindset about this whole problem, talk about likelihoods, this kind of thing, things that statisticians like. So this is what we call doing maximum likelihood estimation, or equivalently minimizing the relative entropy. So let me consider a simple setting where I have a model distribution on a finite set of labels, 1, 2, 3, 4, 5K. So my model distribution is just a vector of size K, B1, B2, B3, Bk. And now, given this model probability distribution, so basically it's the output of my classifier, my current guess on what is likely or not, the likelihood of observing a sample X, so where X can be 1, 2, 3, 4, 5K, is this quantity, just B of X, that I call, a bit, I emphasize L beta of X, the likelihood according to beta of observing X. So that's just for one sample. And now, assuming independence, and I stress that, in mathematics, we always say, yeah, samples are independent, identically distributed. It's a super strong assumption, right? If you take a data set, out of the box, it's very likely that the different rows are correlated to each other. Like, if you look at, my geolocalization data, it's not random samples in Paris, okay, right? There is a very strong time correlation. So immediately you see that, okay, this innocuous looking, assuming independence is very strong, but assuming independence between the different samples, the joint likelihood of a sample x1, x2, xn, so the joint likelihood of observing different values is just the product of the individual likelihoods of any given sample. Okay, that's kind of the definition of being independent. So the likelihood, according to beta of an n sample x1, xn, is b of x1, b2, b of xn. And now in practice, what we can be interested in is to find a sample x1, xn that maximizes the likelihood. Like, we like to understand what does it mean for a sample to be likely with respect to beta. And so the thing is that maximizing this product is equivalent to maximizing its logarithm, because the logarithm is a strictly increasing function. And so because convex optimization is always written with minimizers, we are going to stick to the conventions of people who do optimization, because we are going to use their solvers. So we are going to minimize minus the log likelihood. And so that's what I call small l of beta, x1, xn. It's minus 1 over n, I normalize things, of the log likelihood. So it's 1 over n times, basically, the average value of log of b of x1, b of xn, and the minus, if I take it inside the logarithm, it corresponds to taking the inverse of the probability 1 over b of xn. So that's a quantity that I can compute for any sample. Yes.
Excuse me, what is b? It's a function or
B. So here, I'm in this very simple setting. So B actually is the density of my model with respect to the counting measure on 1K, but it's more that I have a finite set. I have a finite set of samples, 1, 2, 3K, and B is just a function that takes as input a label and gives you its weight. So it fully describes my model distribution beta. I don't know if doesn't seem to be very clear. Sorry.
I think
So you can say B is a vector, and B1 is just the coordinate of this vector that is associated to the first label. So for instance, here, K is equal to 4. And for instance, the red distribution B, or I stick to the same color. So the blue distribution B, beta, is associated to B of 1 is very small, B of 2 is pretty large, B of 3 is small, and B of 4 is kind of large. And the property is that B1 plus B2 plus B3 plus B4 is equal to 1, because I'm a probability distribution. Okay?
Did you say the one for compositional
Yes.
or mathematical reasons?
You have different motivations. Here it's because basically we want to use linear formulas. Basically we like to use a summation operator, and the logarithm is what turns this product that comes from a hypothesis of independence into a sum. So that's why we use it. Okay, so it's good both for algorithms and also for the math. Like, it makes things simple. Just like basically, we use Gaussians. You have many different reasons to use Gaussians, but one of the main reasons is that maximizing likelihood for Gaussians corresponds to minimizing a quadratic function, and minimizing a quadratic function is just solving a linear system. So all of these things are tied together for different reasons. And that's what Gauss understood back in the 19th century. That's why we call these Gaussians. He understood that taking the normal distribution is heavily related to minimizing a least squares problem, which is heavily related to computing the arithmetic average. And computing arithmetic average, we've had a co-evolution of our hardware and of the math, because most advances in computers have been motivated by scientific computing, etc. So basically, it's kind of a chicken and egg question of what is more important. Both are important. It's a good compromise. So basically, the likelihood, according to beta, the stuff that we want to minimize is the average value of, for a given sample, of log of 1 divided by b of xi. And now, what happens if the samples xi are not drawn independently according to the model distribution, but according to a different data distribution, alpha? So now you imagine that basically we had a model, like a Gaussian, something simple, and real life gave us samples, and we assumed that it's a kind of random number generator with a fixed unknown data distribution alpha. Then, when n goes to infinity, what is the typical value of L beta of alpha? You know, the likelihood according to beta of a sample drawn from alpha. Well, it's the limit when n tends to plus infinity of this sum. So we have n terms in this sum. But the thing is that this value only depends on the value of xi. So we can group terms in this big sum depending on how many samples were equal to 1, how many samples were equal to 2, how many samples were equal to k. So we can rewrite this big sum into a sum over the k different values that xi can take of 1 over n times the number of terms in my summation, so the number of I such that xi is equal to k, of a log of 1 divided by b of k. And now, if you assume that the samples are drawn independently from each other according to the distribution A, then this quantity, we can permute the sum and the limit. Basically, the average number of points that are equal of xi's that are going to be equal to k is exactly given by A of k. Okay, and so that's where those terms come from. It's basically this term that is called the cross entropy of A of alpha with respect to beta just appears as the limits of this likelihood function when the number of samples goes to infinity. Okay, so that's L beta of alpha. And this is the thing that we'd like to minimize. Now, in practice, usually your data distribution alpha is fixed. That's your data set. And what we're really trying to do is to find a model distribution beta, which is as likely as possible. A model distribution in a given set of parametric family of functions that explains the data as well as possible. So we want to minimize with respect to beta, L beta of alpha. So, to have neat formulas, we can decide to add a constant term with respect to beta, which is L alpha of alpha. So we define the relative entropy or Kullback-Leibler divergence as the kind of neg log likelihood of alpha with respect to beta minus the log likelihood of alpha with respect to alpha. And so it's equal, you just take this formula and apply it, it's equal to the sum over all different possible values of A of k times log of the ratio A of k divided by B of k. So this formula, basically, it's designed in such a way that the relative entropy of alpha with respect to alpha is equal to 0. Okay, just by construction. This is why we subtracted this L beta, this L alpha of alpha. So which is good because we want to minimize something. If this something is equal to 0 when we have actually reached the objective, probably it's good because it's good. It means that this term behaves like a least square error, like a data attachment term, and then it's going to be convenient because we are going to be able to add it in a big loss function where we're going to have a data attachment term plus regularization term, this kind of thing. It's going to be very dramatic. So first property. Second property is that it's positive, it's non-negative. Basically, this quantity here is always going to be greater than 0, assuming that I have probability distributions. And it's going to be equal to 0 if and only if the AK coincide with the BK. So there are many different proofs of the fact that this quantity is positive. I think the simplest one is this one. So we know that the logarithmic function is concave. So among other properties, if you look at the log and you look at its tangent at x equal 1, you know that the curve of log is always below the tangent at x equal 1. So log of x is always smaller than x minus 1. So among other things, it implies that log of bk divided by ak is smaller than bk divided by ak minus 1. And so now, if I multiply this inequality by minus 1, if I change the signs, it means that log of ak divided by bk, okay, because the properties of the log mean that if minus log is the log of inverse, is going to be greater than 1 minus bk divided by ak. And this is exactly the term that we have in the definition of our relative entropy. So now I take this inequality and I sum it for all values of k with a weight that is equal to ak. Then I recover on the left-hand side, I recover my relative entropy. On the right-hand side, I recover the sum for all values of k of ak times 1 minus bk divided by ak. And now the thing is that I can just expand this formula into a sum of ak minus the sum of the bk's, because the ak divided by ak is equal to 1. So I recover sum of ak minus sum of bk. Both terms are equal to 1. So I get 1 minus 1, which is equal to 0. Okay? So that's very simple proof of the fact that the Kullback-Leibler divergence is positive. So it kind of behaves like a distance, or at least it's good enough to be used as a loss function in logistic regression. Now, the first properties of this formula. Well, first is that we can define it for continuous distributions. Okay, the Kullback-Leibler divergence between alpha and beta, we define it on histograms, but we can also define it between distributions, for instance, between two Gaussian distributions. It's completely fine. We replace the sum with an integral, and then we have the density. What is important is this definition is that the density ratio, like the Radon-Nikodym derivative, should be well defined. Otherwise, it's equal to plus infinity. Now, okay, so it's fine. It's usable as a loss function, but keep in mind that it is not symmetric. Okay, so you can remember it as the relative entropy of data with respect to a given model. Okay, so that's the order in which they appear. So another thing is that it's, I emphasize that it is tied, the use of relative entropy is tied to an assumption of independence. Yeah. If your samples are related to each other in a strong way, probably it's not an excellent tool. Like it stops being the best tool in town. The thing is that historically, you know that relative entropy, all of these things, were introduced. Basically, we remember a paper of Claude Shannon, that introduced these things in the computer science applied math literature. And basically, this whole literature on entropy information geometry, information theory, was heavily motivated by compression problems on communication networks. It was really designed in this setting where you are the telecom network, like the Bell company Orange in France, or France Télécom. And basically, you assume that users are sending you packets of data. You want to compress them, send them efficiently, and decode them on the fly. And so in this setting, it's kind of reasonable to assume that all the data packets that people send you are independent from each other, because you have like a few million people sending you data packets. So you just know what is the typical distribution of those data packets. Like, for instance, you know that there's going to be way more text ASCII characters sent than strange ASCII characters like arrows or even punctuations. So you have this statistical knowledge, and by leveraging this statistical knowledge, you want to design effective compression algorithms. Okay, and if you do the math, if you go to the very end of this, you end up essentially with a zip format, like the zip algorithm. So
with zip, there is no loss in the compression, whereas here we are talking about probability and so on. So it's a bit strange, isn't it?
And also, okay, so I skipped this. Okay, the idea is that the entropy of a data distribution is a way allows you to describe how much you can compress a byte stream without making any losses. And the standard interpretation of the relative entropy in this context is it's a measure of suboptimality. So the idea is that you have designed a code, you have designed an algorithm given some model on the distribution of byte streams. So you have designed your algorithm, and then the real life distribution is a bit different. And the KL of the real data distribution given the model actually tells you how suboptimal you are. So it's equal to 0 if you have a perfect code, and typically it's a bit larger than 0. So that's a standard interpretation. It's not super relevant, so I had planned to make slides and then I realized, okay, we don't really care today. So that's the idea. I mean, it's very important, obviously, and foundational topic. And so you can think of the relative entropy as a zip of distribution geometry. Okay, zip, it's definitely very interesting to have it in your toolkit. If you have text, maybe it's the best thing you can do. If you have images, basically it kind of corresponds to PNG files, but if you have a photo, you know that you shouldn't use this. You should use JPEG or JPEG 2K, something that leverages the structure of the data more than an off-the-shelf lossless compression algorithm. That's really the picture that you should have in mind. So crucially, if you look at this formula, you realize that the relative entropy first pays 0 attention to the distances between labels. Okay, just like the total variation, it doesn't care about the fact that a tiger is close to a lion. Okay, it doesn't appear, and in some senses, it can be a desirable property because many times in data sciences you don't really understand your label, so you say, okay, I don't understand what I'm doing, I'm going to use it. That's the idea. On the other hand, and that's the main difference between the total variation and the relative entropy pays a lot of attention to unlikely events. And if an event actually appears in the data, like if AK is non-zero, then your model should better have affected some density, some probability to this state. Okay. Because this log of AK divided by BK can clearly blow up. So maybe what happens is that, for instance, if an exceptional event appears because AK is non-zero, and if BK is equal to 0, then here in the logarithm you have log of something positive divided by 0. So you get log of plus infinity, that's plus infinity. You get massive penalty. Okay? So in this context, basically the relative entropy believes that prediction 2 is much better than prediction 1. Okay? That's the picture that you should have in mind. Because prediction 1 basically was too confident that this was not a lion. It was a major mistake. Basically, you get plus infinity penalty. So that's the first property to have in mind about this. So, but okay, where is the geometry in there? If you want to get a geometric intuition of the relative entropy, maybe a good picture to have in mind is to look at the geometric structure that it induces on a set of probability distributions that you know well. For instance, the set of one-dimensional Gaussian distributions. So this is what people call studying statistical manifolds. And the relative entropy in this context is called the Fisher-Rao metric. So let me consider the Gauss maps. The things that we always write with a nice n. Okay, we always write, let me consider a Gaussian distribution n of m sigma squared. Yeah, I should have put the sigma squared for that. maybe you see it as just a notation, but it's actually an application that takes as input a mean value, like a real valued mean value, a standard deviation, or equivalently a variance, and generates a probability distribution for you. So it's a map from a 2D space into an infinite dimensional space. Basically, and the Gauss map kind of defines, the picture you should have in mind is that it defines a surface in a very complex space. And the question that we ask ourselves is, okay, I have defined a distance in this very complex space, in the space of probability distributions. What kind of geometry does it induce in my 2D plane of parameters m sigma? And maybe, for instance, if I display those Tissot's indicatrices, if I understand distortions, it's going to allow me to get some intuition of my infinite dimensional space. So, out of the box, it's a bit cumbersome because the relative entropy is not symmetric, so it does not really define a distance and all that. But the way we do it in statistics is that we say at least locally it's symmetric. Basically, what we can do is compute the relative entropy of a Gaussian of mean value m plus dm and of standard deviation sigma plus d sigma against the standard Gaussian distribution of mean value m and deviation sigma. So it's a formula, you have logs, you have exponentials, because you have exponentials in the definition of the Gaussian. And so if you do the math, and if you're interested, you can just click on this link. It was a typical exercise in a workshop that I gave at the École Normale Supérieure. You can see that it's equal to this quantity. So the relative entropy of a Gaussian distribution up to a small perturbation dm d sigma is equal to 1/2 of dm squared plus d sigma squared divided by sigma squared plus a negligible term, plus a term of order more than 2. So locally, you have this expression. This is the geometry that the relative entropy induces. And that's why we spend so much time on the Poincaré metric in the previous lecture. We actually recognize the Poincaré metric on the upper half plane. It's exactly the expression of the Poincaré metric, of the squared Poincaré metric, up to a rescaling of the mean value. Okay, there is a factor 1/2 that you can get rid of if you replace m with m divided by square root of 2. Okay. So that's quite remarkable because out of nowhere, basically thanks to its invariance to translation scalings, because the relative entropy does not care about the actual distance between points, so it's very invariant to the reparametrization of the real line that we could do. The relative entropy induces a hyperbolic geometry on the surface of Gaussian distributions. And that's what is summarized here, in this picture that I already showed you in the previous lecture. So what does it mean? Like, what am I displaying? So here you have the space of parameters for my Gauss map. You have a mean value that can take any number on the real line, and a deviation which is non-negative. So each point, m sigma, corresponds to a Gaussian distribution that I display here. So for instance, this point, mean value around here and very small deviation, corresponds to a very peaky normal distribution, like the very red one. This point, like mean value around here and large deviation sigma, corresponds to a very flat Gaussian distribution. Okay, and finally, this point corresponds to a kind of medium-sized Gaussian distribution, which is displayed here. And basically, what this result shows you, if you combine this small computation that you can do on a sheet of paper plus what we saw in the previous lecture, then we see that as far as the relative entropy is concerned, if you restrict the relative entropy, if you restrict yourself to to a path that should, to a geodesic path that should always be a Gaussian distribution, then the shortest path between this Gaussian and this Gaussian, goes through a state where you have a very high variance. Okay, we do not interpolate linearly between, for the mean value and the standard deviation. First, we lower the confidence. So we go from a very small deviation to a very large deviation. So that's what's represented here, like the peak widens. Then we translate, and then we gain confidence back. Okay, and as I told you, it's not absurd, like it's a behavior that you may want to have in your algorithm. As a bit of a joke, I told you maybe the real line is a spectrum of political opinions, and maybe this just describes how people go from being like hardcore communists to pretty confident right-wing voters, And the way you do that is you do not go from hardcore communist to convinced socialist to mild Macronist to very very mild Republican. What generally happens is that you have strong convictions, then things happen, you lose your convictions, and then later on you gain new convictions. So I don't know if this is really what happens for political opinions, but probably for customer choices, interests, like people, I know me, when I'm on YouTube, I'm very focused on one thing one week, then I say, oh, what am I going to watch? And then next week I'm going to watch something else, Maybe this is a type of behavior that happens for quite a few probability distributions in real life, okay? So keep in mind that this is a type of behavior that you're enforcing whenever you use a cross entropy or relative entropy. Good, but okay, that's fine, but maybe you say, okay, come on, like hyperbolic stuff are nice, but I want simpler behaviors. It seems a little bit far-fetched. And so now I'm going to show you two other methods, two other ways of defining distances between probability distributions that are much that provide much simpler flat geometric structures. So the first idea is to try to be compatible with the addition, because when we have probability distribution, we can add them together. So maybe it would be good to have a distance that respects that. What we can do is simple. We can say, okay, I have a source distribution alpha, like my weighted sum of delta xi's, and another target distribution. Okay, and I represent them as, let's say, point cloud or histograms in 2D. But let's say here in this example, I work in a two-dimensional space. If I want to define a distance between those two objects, maybe I can just say those are images. I'm going to use the squared Euclidean distances between my histograms. And it's not a great idea, because if you do that, basically, if the distributions do not perfectly overlap, you're not going to get meaningful values and gradients. Okay. Recall that if we have discrete samples, the likelihood that two discrete samples fall on exactly the same location is very small. So instead, what you can do is you can try to create interactions between points by blurring your distributions. Blurring, we've seen, it's equivalent to adding random noise or to making a convolution with a density function. So what we decide to do is we pick a symmetric function g, and we define the distance between alpha and beta as the squared Euclidean norm, the squared Euclidean distance, between the function g convolved with alpha and the function g convolved with beta. So this squared Euclidean norm, like L2 norm, is just the integral for all positions in the plane of g convolve alpha of x minus g convolve beta of x. The picture that you can have in mind is that, okay, here I had two very sharp distributions supported on curves. Then I blurred them with a kernel, G, and so I created overlap between the two functions, and my loss function is just the square Euclidean norm of this function that takes both positive and negative values. So it's something that is clearly a norm because it's equal to 0 if and only if G convolved with alpha is equal to G convolved with beta. So if your filter is not degenerate, it's going to be 0 if and only if alpha equals to beta. So that's nice definition, and on histograms, that's all you need to do to compute it. If you have data samples, in a high-dimensional space, you do not want to clusterize and to voxelize your space. So instead, you're going to rely on a small mathematical identity that tells you that this formula is exactly equal to the product between the measure alpha minus beta and k convolved with alpha minus beta, where k is a function that is G convolved with itself. Okay, so it's something that you prove by doing a change of variables. The only thing that matters to us is that this expression can be expressed as the sum of 3 double sums. Okay, so it's really the kind of thing that you prove by computing integrals, or you could prove it using Fourier transform. That would be more elegant, but a bit more arcane, maybe if you're not familiar with Fourier analysis. The only thing that matters is that if I have my source distribution alpha, my target distribution beta, I can define this kind of quadratic formula as basically I consider all pairs of points. So first I consider all pairs of points that belong to the source distribution. So I consider all points A and all points J. Basically, I compute how far away they are from each other using the kernel function, and I weight it by the product of the weights AI, AJ. Then I do the same thing in the target distribution, BI, BJ, K of YI, YJ. And I also compute with a minus sign the cross interaction term. So I take random points in the source distribution, random points in the target. I compute K of XI, YJ. I get this, okay, and then I just sum those 3 terms, and it's really equivalent to computing this squared Euclidean norm. Okay, so I mean, we don't have time for the lab session, unfortunately, but I advise you to look at it because maybe the first time you see it, it seems very strange, but actually it makes a lot of sense. For instance, it's a formula that has deep interpretations. Maybe my favorite one is to say that it's equivalent to a Coulomb energy or a Newton energy. This expression is exactly the kind of things that you would get if your source distribution, you think basically they are protons at positions xi with a charge ai, which is positive, and the targets are electrons with negative charges, bj, j. And then physics tells you that you have a kernel, which is, in real physics, it's something like 1 divided by the distance, okay, the Coulomb kernel. And this expression is just the total energy of my configuration. And if you have protons, electrons, that this total energy is going to be minimized if you have an overlap between the two distribution of charges, because positive and negative charges attract each other. So using those kind of formulas as loss functions is kind of equivalent to simulating a physical system, and that's fine. So from a mathematical perspective, maybe those kernel norms have a long history. Okay, they've been studied in many different communities. They are called Hilbert or Sobolev norms in functional analysis. In statistics, over the last decade, people have called them maximum mean discrepancies or reasons. The important properties is that those formulas, they are quadratic with respect to the weights, AI, AJ. So it really looks like a squared Euclidean norm. And they are compatible with the addition. So you can show that the geodesic from alpha to beta, if you have two distributions, the geodesic thing is just you interpolate linearly the weights. So 1 minus t alpha plus t beta. So the trajectory you should have in mind between two Gaussian distributions, that you had one Gaussian, well, it slowly fades away while the other one grows. Okay, maybe it's not exactly the behavior that you want to have, but at least it's simple. So it means that it's going to be easy to implement. Now, a caveat is that when we look at those mathematical properties, we do not really see the influence of K. All of these properties, they hold if K is a Coulomb kernel, a Gaussian kernel, an exponential kernel. And I think that especially among people who do theory, people believe that those formulas are all equivalent to each other. It's completely false. Okay, and so that's something that I think you should experiment with. So that's one of the main topics of the lab session, show you that depending on what you want to do, for instance, Gaussian kernels are arguably the worst choice that you can make. Okay, and it's important because I think when people think about kernels, they immediately think Gaussian kernels. Warning, Gaussian kernels are fine if you want to emulate very local interactions, but if you want to have global convergence of point clouds, it's terrible. Okay, you'd much better use something else. And they are very good kernels that produce these behaviors. So crucially, okay, those formulas are the first one that I showed you that actually pay attention to the structure in the space of features, in the space of labels. So if you define a good kernels on the space of animals and planes, you can get a behavior where predicting a tiger is not so bad if it was actually a lion. So that's the first thing. And also, because of the structure of this formula, out of the box kernel metrics, they pay little attention to unlikely events, because you have products of likelihoods. So if the likelihoods are small, this product is going probably to be very small, except if K of xi, yj is very large. So basically, kernel norms, they only pay attention to unlikely events if they are associated to outliers. Like basically, if an unlikely event corresponds to very strange values of the features, then this is going to be penalized. Okay, so basically a kernel norm, if you use it for a classification task, it's going to promote basically prediction that are in the good region of the feature space. You're going to be very harsh on predictions of features that are completely out of the reach of observed data sample. So that's one thing, but we didn't recover a super nice linear interpolation, right, between Gaussians. Basically, when we switch from Kullback-Leibler to kernel norms, we just change the behavior from this change of confidence into a fading interpolation. And maybe what we want to have instead is really a translation of the Gaussians. And if you want to get this behavior, then probably you should use optimal transport theory. Okay, optimal transport is the theory, the formulas that are defined to be as basically optimal transport metrics are formulas that are as faithful as possible to the metric on the ground space while keeping computation simple enough. Okay, that's the main motivation. So out of curiosity, like how many of you follow the lecture of Gabriel Perret on optimal transport? Okay, so quite a few, but not everyone. Okay, so good. Okay, it's interesting. See that I would have assumed that there would have been a very strong correlation, but actually no, which is interesting. I would like to look at the statistics at the end of the year. So personally, I've worked a lot on optimal transport, and whenever I want to introduce it to people who are not familiar with it, I say that this is what generalizes sorting, quick sort, those kind of things, to spaces of dimension more than one. Because you know how to sort values on the real line, but sorting 2D points, 3D point clouds, high dimensional point clouds, it's not clear how you would do it in a way which is fully isotropic, without using a lexical order. So how do we manage this? Well, let's consider 2 point clouds, A. So A, it's x1, xn, B, it's y1, yn. so two discrete samples of n points in RD. We define the optimal transport distance, the squared, it's called the Wasserstein-2 squared distance between A and B, as the squared Euclidean norm, like this quantity, the average value of xi minus yi up to permutations. So basically, if the permutation is the identity, this is just the squared Euclidean norm between the point clouds. But remember that measure theory probability distribution unit should be invariant to permutations of the points. And so this is a permutation invariant equivalent of the squared Euclidean norm. So out of the box, it looks like a complex combinatorial optimization problem over a set of cardinal like n factorial. But fine. At least an interesting property of this formula, of this least squares energy up to permutation, is that it allows us to define the notion of sorting or increasing mapping without using the ordering structure of the real line. So why is that so? Well, assume that my two samples, x1, x5, y3, y1, y5, okay, they lived in a two-dimensional plane, but actually they lay along straight lines. So they are really one-dimensional objects. Then you can show that the optimal permutation is exactly going to correspond to an increasing coupling between the two point clouds. Basically, the permutation sigma that minimizes this quantity is the one that maps x1 to y3, x2 to y5, x3 to y2, x5 to y1. And a way of seeing this is that imagine that there was a crossing. Imagine that my optimal permutation was assigning x4 to y2 and x3 to y4. Then it's not too hard to see that, okay, here maybe you would decrease the cost a lot, but by introducing this long coupling between x3 and y4, you're actually losing a lot because the squared Euclidean distance is strongly convex. So it's always a bad idea to introduce crossings. And so this is why in 1D, the optimal coupling has no crossing. So in other words, it is an increasing mapping. Okay. Another way of saying this is that the optimal coupling always corresponds to the gradient of a convex function. And in 1D, the gradient of a convex function is an increasing. So that's the picture. It's one of the motivations to study optimal transport. And in general, okay, we do not, dealing with finite point clouds, combinatorial algorithms is very complex. So we like to recast the optimal transport problem as a linear optimization problem on a permutation matrix. So let's consider like a weighted point cloud. So now my point xi has weight ai, my point bj has weight yj. Then you can show that this quantity, basically it's equivalent to the optimum of this minimization problem with respect to a full n by n coupling matrix with constraints that encode the fact that it should be a permutation matrix. So the constraints tell you that the transport plan P should be non-negative, and it's basically each source point should be transported onto the target. Okay, and maybe at first it's look cumbersome because okay, I had a very simple thing, object that I understood. Now it's strange. I have a large variable. Yes, okay. Linear optimization is a bit frightening, but linear optimization is convex. It's easy. It's easier to study a simple optimization problem on a large variable than studying a terrible combinatorial algorithm, combinatorial problem on a small variable. So that's an insight from optimization theory. So alternatively, okay, you can understand optimal transport as nearest neighbor projection with a constraint of incompressibility, because this is essentially nearest neighbor. Sigma is essentially a nearest neighbor projection with a constraint that it should be bijective. So you cannot send 2 points at the same location. So you cannot squash your source point cloud onto the target. You have to spread mass evenly. It's also like, it's one of the very fundamental example of a linear program of the transport plan PIJ. So in the history of optimization theory, it's a very important problem. And as far as we are concerned, you know, as data scientists, this theory induces two main quantities. Well, first, if you have two distributions, you compute this transport plan, this increasing optimal mapping between the two distributions. And that can be interesting. But today, for us, you know, what we're really interested in is just the value of the costs. This OT of AB, this squared Euclidean distance up to permutations. This is called the Wasserstein-2 distance, and it has quite a few nice properties. But maybe just to be clear on what optimal transport looks like, here I show you a few examples, okay, of optimal transport between a source point cloud that I color using rainbow colors and a target, okay, which is in blue. Like here, I am matching like a potato with a saxophone. And to display the optimal transport coupling, you know, I show you the end, basically the target of every point, you know, using a color scheme. So what you can see on this image, okay, like for instance, that this point gets sent here, these points, the red points get sent here. You see that optimal transport, at most locations it's smooth, and it really matches the two distributions together, but it's not smooth everywhere. Okay, and that's very important. You have no guarantees of preservation of the topology. Here you see this because this disk, the red disk here, was split in two parts. Here you have one part, here you have the second. Okay, so that's essentially that. Personally, I think optimal transport is the best thing you can do with very simple math. Basically, we're going to see that as soon as you try to enforce preservation of topology, it gets more complicated, more costly numerically. So optimal transport is kind of a first step towards this, but without strong guarantees. Yes?
Can you ever use these ideas in a setting where you're not starting with the same ends? So like some points can be split and assigned.
Yes, totally. You know, because it completely supports weights. Actually, you can define it using density continuous distribution, so it's completely doable. Can also handle outliers, everything. You know, here I'm just showing to you the most vanilla version of it. I'm already showing to you so many formulas. I have to keep things simple. But yes, I mean, totally, it's something that has been studied extensively. So everything you want to do, we know how to do it. It's just that enforcing topology preservation kills the convexity of the problem, so it becomes much more complex. That's kind of the fundamental problem of shape registration. But yes. So, okay, but anyway, we can map potatoes to croissants. We can do anything we like. Okay, and so typically those kind of images, you know, people like to see them in the machine learning literature, especially, you know, for generative models. It's exactly the kind of picture that people want to see, so that's fine. In shape analysis, if shapes are close enough to each other, it can be good enough. Okay, and that was the spirit of what I talked about in the lecture about geometric deep learning. I showed you essentially now with point neural networks, it's easy to register shapes to a near fit, and once you are this close, optimal transport gives you a pixel perfect fit. It's kind of a good combination of methods. But you should always keep in mind that, okay, we have no preservation of topology. And so, for instance, this is a typical counterexample for optimal transport theory. Here, I am mapping one croissant, one moon, onto another one. And what you see here on this plan is that the mapping behaved kind of like a one-dimensional sorting along the x-axis. It didn't match this end to this end, and this end to this end. Like this part of the first croissant was sent here in the middle. Okay, so optimal transport here actually splits, cuts the thing in two. So it's important to keep this in mind that if you use optimal transport to estimate large deformations with those kind of XY features, very simple features, yeah, you're not going to get something that is smooth deformation. If you wanted to use optimal transport to do shape registration, probably what you should do is you should embed your points in a high dimensional space, for instance, by adding a z coordinates that corresponds to the curvature. Because if you do that, then maybe the ends of the shapes start to be closer to each other. So in a separate thing, you make the problem easier by adding more and more features. Okay, and so that's how we think of it in shape analysis. But okay, that was for what it looks like. Yes.
So if the purpose is to fit the two disputes, if it's I don't know. I feel it's the two things is kind of mixed. The two objects with kind of mixed. So one is to fit to define distribution, and also the another thing is the original like clear the family structure is kind of mixed after
Yes.
transportation. But if the motivation is to fit to think
So yeah, so no, it depends on what you want to do. It's just that I think, optimal transport, there is optimal in the name, and so people assume that it's great. It's a generalization of sorting. Sorting, it's important. And with sorting, you can match 2-point clouds together, no questions asked. The thing is that you should dampen your expectations. Just because you are smooth most of the time doesn't mean that you cannot have tearings. And with optimal transport, it's very well documented. The transport plan is not smooth everywhere. And I'm just telling this to you because I think it's not clear in the name. That's it. I also think that, as far as simple mathematics are concerned, optimal transport is kind of expensive. It's kind of an advanced topic. If you're used to just kernels or the relative entropy, it looks like something that is desirable. And I think in the machine learning community, people treat it as a very strong object. But personally, I come from a different perspective. I come from the community of people who deal with like physical models, topology preserving models, and from this perspective, optimal transport is actually very cheap. It's I would say it's the first model that starts to look like a geometric distance. It's the first thing that starts to preserve, to be faithful to the geometry of the space, but you really lack all those desirable properties that people see in toy examples. So, just about that, like optimal transport is an important object because it is at the intersection of many different research communities. And so, if you look at it from the perspective of I have a simple, I'm only used to closed formulas. This looks cool, great. But if you look at it from a perspective of I'm used to super accurate deformation models for the heart, optimal transport, the optimal part of the name really looks like overhyped. So, and I'm saying that after having spent years, I think it's a very interesting object, but I should be honest. Yes.
Can you generalize square transfer when the 2-point clouds are not the same dimension?
So the same number of points completely, the same dimension, like they do not live in the same space. No, it's a different problem. So, and that's what I'm going to show you in kind of the open problems. So people can want to define optimal transport-like distances in this setting, like Gromov-Wasserstein and all that. It's orders of magnitude more expensive. So, it's still open. So basically, I'm talking to you about optimal transport because now it's solid, it's easy to compute. All the other things are more like work in progress. Maybe in 10 years, it's going to be easy, but whatever. Yes, so now, okay. A good desirable property of optimal transport is that if you forget about moons, crescents, if you just stick to Gaussian distributions, everything looks perfect. For simple distributions, it's really perfect. So let me reconsider, my Gauss map from that takes a mean and a standard deviation and generates a probability distribution. Then I can show very quickly that, up to this factor 2 that I introduced everywhere in my formulas, because I like to have clean gradients, but up to this factor of 2, the Wasserstein distance, or the squared Wasserstein distance between a Gaussian distribution of mean M1 deviation sigma 1 and a Gaussian distribution of mean M2 deviation sigma 2, it's just the squared Euclidean norm, M1 minus M2 squared plus sigma 1 minus sigma 2 squared. So, and it means that if I have two Gaussian distributions, like this one, then the geodesic interpolation for optimal transport is just the linear interpolation of both the mean value and the standard deviation. So maybe to model political opinions, you don't want to do that, but at least for me, if I want to model the displacement of 3D point clouds, or for people in physics who want to model the flow of particles, it's exactly what we want to, it's exactly the behavior that we want to have. And that's why there has been so much emphasis on optimal transport of the past decades. Okay, so optimal transport gives you the Euclidean metric on the upper half plane. So it really lifts the geometry on the sample space, like between mean values, to a set of Gaussian distributions. So I'm showing this to you to tell you that there is no metric which is better than another one. The Euclidean metric, it's simpler, but the key insights from geometers from the 19th century is that Euclid is not alone. Okay, the other geometries like the Poincaré metric are just as legitimate. It just corresponds to a different prior. And so now we've seen that just on the set of Gaussian distributions, you have at least two canonical distances. Basically, looking at Gaussians plus the Wasserstein metric, it's Euclidean geometry. And looking at Gaussians with a relative entropy, it's hyperbolic Poincaré geometry. Okay, that's fine. For me, it's very strong motivation to study both. But maybe that's because I'm a mathematician. Now, another cool thing is that once you have a distance between probability distributions, you can define an interpolation. Because making interpolation is just like solving a least square problem. The average between 4 different distributions is going to be the distribution that minimizes the sum of the distances to the 4 different samples. So that's what we call computing a Fisher mean. And we say that, for instance, the barycenter of a collection of 4 different distributions, B1, B2, B3, B4, is the argmin of this kind of term. So here I'm showing you what happens when B1 is this distribution, B2 this one, B3, B4. So here, black means no mass, and white means that there is mass. And here, those are the barycenters, the Fisher means, when the loss function is a kernel norm. And the thing is that because the kernel norm is compatible with the addition, the Fisher mean is just going to be a pointwise addition, pointwise norm. So, okay, kernel norms correspond to local fadings. So maybe it's not what you want to do if you want to do geometry. Maybe you would prefer to have those kind of smooth displacements. And so this is what is given to you with the Wasserstein metric. So that's one of the main motivations for me to study optimal transport, is that we know that solving this problem is easy. Now we have very fast solvers. And this is exactly the type of things that we would like to have in computational anatomy. So now the thing is that, okay, I've talked to you about the Wasserstein distance, but I didn't tell you how on earth we are going to solve this problem, because it looks very hard. Okay, right? If we have endpoints, it looks that we are optimizing on an n by n matrix. So it doesn't look very scalable. And this problem has been very strong motivation in applied mathematics since the 1940s. So, I think at least if you look at the literature, every decade you have progresses that's being made. So for instance, back in the 1940s, you have Leonid Kantorovich, who understood that you do not have to work with a large n by n matrix. It's possible to work with dual variables that are just vectors that have the same memory footprint as your input data. And so basically it's possible to solve the optimal transport problem with a linear memory footprint. So it's possible to imagine that if you wait long enough, you're going to be able to solve an optimal transport problem with n equal 1 million. Because 1 million by 1 million in memory, it should be a terabyte, and no one has a terabyte of RAM except in clusters. So that's one thing. Then, okay, you have people in the 1950s who showed cubic algorithms that solve the problem exactly. So that's fine. And you can show that in the general case, if your point clouds are high dimensional and if you want to get the exact solution, maybe it's the best you can do, like cubic time. But at least in our applications for machine learning, we do not really care about having the exact permutation. If we get a permutation that is very close to being optimal, that's fine for us, especially if we're only interested in the value of the distance. And if you accept to relax your criterion on what it means to solve the optimal transport problem, then people in the 1970s, like Dimitri Bertsekas, they showed that it's possible to solve it in quadratic time, O of n squared. So that's the auction algorithm. And then people studied the auction algorithm, studied a softened version of the auction algorithm, which is called the Sinkhorn algorithm, with simulated annealing, like great papers from the 1990s, from the early 2000s. And so, for instance, in 3D shape analysis, using Sinkhorn, like using optimal transport as a loss function for registration problem is completely standard. Like you have Wikipedia page on this. I mean, everyone knows that it exists. And that was the state. And then what happened 10 years ago is that you have GPUs started becoming usable by mathematicians. Okay, so basically 10 years ago, you have Marco Pichuri who realized that we could use GPUs to implement those algorithms very effectively. So actually, he rediscovered the algorithm because, like many people, he found that it was a good idea. And it really prompted a massive interest in optimal transport in the machine learning community over the last decade. But meanwhile, people, especially closer to physics, like Quentin Mérigot, Bruno Lévy, Bernard Schmitz, they progressively understood other ideas, which are that, sorting in dimension 1, that you have log linear algorithms. And since optimal transport is just sorting in dimension 2, 3, 4, 5, 10, we desire to have this log linear complexity. And they show that if you invent multi-scale solvers, it's possible. At least for if your distributions have a geometric structure, like typically in dimension 2, 3, 4, no problem, it's possible to get log linear runtimes. And so you have all of this happening in the past decade. Basically, people using GPUs, developing log linear runtimes. And so, for instance, a lot of work that I did during my PhD thesis was to understand all of this and to merge them together. And now what we have are algorithms like multi-scale Sinkhorn algorithms implemented in a GPU that really behave like generalized quicksort algorithms to solve the problem. So we have log linear runtimes if the dimension is small, and quadratic runtimes otherwise. And anyway, in very high dimensional space, the matrix of distances has little structure. So you cannot guess ahead of time what the coefficients are going to look like. So it makes sense that runtimes will be at least quadratic because you're going to have to evaluate all the distances between points at least once in a high dimensional space. So that's the idea. And the thing is that, okay, today, optimal transport clearly scales up to this kind of anatomical data, like 100,000 points, 1 million points, it's not a problem anymore. So with a precision of, if you're interested in computing a Wasserstein distance with a precision of 1%, a gaming GPU, what you can do is you can install this library that I'm still developing. Okay, I should develop it more in the next few months. With a modern GPU, you can handle those kind of point clouds with 10,000 points in 50 milliseconds and 100,000 points in a fraction of a second. So optimal transport that was a bit of a dream 10 years ago, now it's completely on the shelf. for people. So, and that's because the whole community has worked a lot to achieve this. So now, if I recap all of what I told you about those classical distances between probability distributions, then what do we have? Well, first we have the total variation, which is invariant to the ground metric on the space of labels and only cares about large weights. Then you have the relative entropy, which is also invariant to the ground metric, but which actually cares about exceptional events, because it cares about the ratio between the actual density and the prediction, AI divided by Vj. So that's for the things that you want to use if you do not understand your space of labels. Now, if you understand the geometry of the space of labels, probably you want to use instead geometric divergences, geometric distances. And the two main families are kernel norms that are more or less faithful to the ground metric, depending on the kernel K, and optimal transport distances, okay, that are extremely faithful to the ground metric, that were expensive to compute even 5 years ago, but now it's rescalable, at least if you're working in a Euclidean space. So it's still an open problem to get super scalable solvers if the distributions are supported on a graph or on a manifold. But let's say for most use cases, it's now as efficient as anything. So I think this is like the toolkit that you can take with you to try to define loss functions between distributions. And now to finish, I'm just going to tell you what current research is about, okay, in this field, now that we have achieved what we wanted with optimal transport. Well, the first one is, can we define topology-aware distances? Okay, because I showed you that optimal transport does not preserve the neighborhood structure, and neither do kernel norms or the Fisher-Rao metric. So can we define an optimal transport that preserves the neighborhood structure, that transport distributions, but making sure that neighbors in the source get mapped to neighbors in the target? So it's a problem that has been studied for decades. Okay, in optimization, we call that the quadratic assignment problem, when optimal transport is a linear assignment problem. In optimal transport theory, they talk about the Gromov-Wasserstein distance. Obviously, it's very important in fluid mechanics because saying that you want to preserve the topology of a point cloud is a bit like saying that you had 4 points on a grid and then you had some kind of fluid evolution that distorted the space and preserved the fact that those 2 points are close, etc. So you have a very strong link to the literature in physics, like with the Kamasa-Holm equation, geometric interpretations, and the Euler equations. Personally, in shape analysis, it has been a massive topic for the last 25 years. And some of the metrics that people have defined, like LDDMM, SVF, that are basically explained by Alain Trouvé, in the second semester, actually work. Like basically, those ideas, like optimal transport plus topology preservations, are behind the software that people use to register brain images together. And so this is whenever people do analysis on functional MRI data, you have to deal with the fact that my brain does not look like your brain. Our brains have different shapes, and to put all of our brains together in a common coordinate space, people use those kind of ideas to find diffeomorphic matchings between brain images. Okay, in statistics, nearly exactly the same ideas are called doing Stein variational gradient descent, and in deep learning they call this doing neural ordinary differential equations. So just to tell you, it's very active. I do quite a lot of work on this topic, and as of today, well, major tools exist. We understand a lot of things, but you have to keep in mind that all of this remains at least 2 orders of magnitude slower than optimal transport. That's a bit of a shame because basically, if I give you 2 big distributions, it's going to take you maybe 1 second or 5 seconds to compute the registration. And if something takes 1 or 5 seconds, it's fine. But if it takes a few milliseconds, it means that you can go to a higher level. It means that you can use this distance to compute UMaps. You open up new possibilities. So, I mean, topology preservation is always going to have a cost. So no one expects those kind of methods to be as fast as optimal transport, but at least getting closer to 10 times, basically to just one order of magnitude would be great. So that's what we are really pushing for in our research. Open problem 2, as always in this lecture, is the curse of dimensionality. Okay, the fact that in high dimension, the matrix of Euclidean distances stops being informative. That's what we saw earlier in many different lectures. And so all the standard kernels or optimal transport metrics that I showed you are completely overwhelmed by statistical noise. Basically, it's useless to say, I use a Gaussian or I use a squared Euclidean distance if your squared Euclidean distance are just constant plus noise. And we saw that this is what happens with white noise. So nevertheless, people want to define distances between high dimensional samples and compute gradients. This is what generative modeling is all about, GANs, variational encoders. So how can you do this? How can you compute meaningful distances and gradients in high dimensional spaces? Well, there you have really a fundamental insight from functional analysis, which is that working with measures, distributions, is a bit like working with continuous functions. And sets of continuous functions correspond to distances between measures. So the name that's given here, in the mathematical literature, we say that a distance between alpha and beta can be computed as a maximum of alpha minus beta f. So basically, you take the maximum over all functions f in some set B of the difference between the integral of f with respect to alpha and the integral of f with respect to beta. Okay, and this is what mathematicians call a dual norm. And in statistics, people call this a maximum mean, because you have an integral here, so it's a mean, and discrepancy, because you have a minus sign. So this is where the name maximum mean discrepancies come from. And in the deep learning literature, people call this an adversarial norm. Okay, the adversarial in GANs refers to this. Okay? Refers to the fact that if you have data samples, and if you want to compute a distance between them, then maybe what you can do is you can define a class of test functions f and look at how well you can distinguish between alpha and beta using integrals with respect to f. The thing is that once you have defined your loss functions using this formula, then in practice, we look for values of the parameter of our generated sample that minimizes the distance between alpha and beta. So during training for a generative model, we typically solve this kind of optimization problem. Argmin with respect to theta, so argmin with respect to the parameters of my neural networks, of the maximum for functions f in a class of functions of alpha of theta minus beta f. Okay, this is a min-max problem that, for instance, I mean, if you've ever read anything on GANs, this is the first equation. And this, just to tell you, what is new with GANs is to say we're going to use neural networks to try to do this, but this idea has been studied extensively in math since at least the 1950s. And we have a lot of insight on what happens. First is that all the classical things that I showed to you, all the classical norms, total variation, kernel, even relative entropy, can be defined this way. You can always identify a distance between probability distributions with a set of test functions. And so, for instance, the total variation norm is what happens when you take as a set of test functions the functions that are bounded between -1 and 1. Okay, the total variation between alpha and beta is the maximum for all functions f with an infinity norm smaller than 1 of alpha minus beta f. And you see that this definition, there is zero geometry. Okay, when you define the infinity norm on set of functions, you do not take into account that x is close to y. It just says the infinity norm is the maximum over all possible values of the absolute value of x. And so you have zero geometry, so we always saturate on disjoint samples. Why? Because if my two distributions, alpha and beta, if their supports do not overlap, then I can define a function f, which is equal to 1 on alpha, minus 1 on beta. And so I'm going to get something which is equal to 2 here by splitting the integral in two terms. So that's really and if you take a lecture on functional analysis, it's all about this. It's about telling you that if you have too many test functions, your norm essentially is gibberish. And so the whole game is to constrain the set of test functions to define interesting norms. And we call this functional analysis because it's super relevant for the study of partial differential equations. Now, so for instance, one main way of doing that is to consider Sobolev norms. So you consider the set of functions whose integral that are squared integrable and such that their gradient is squared integrable. And so you look at functions such that this quantity is the integral of f squared plus the integral of gradient of f squared plus maybe other derivatives is smaller than 1. And if you do that, the dual norm that is associated to this is exactly a kernel norm. So as you can see in the lab session, you have some artifacts with that, but generally speaking, in small dimension, it's kind of relevant, because a smooth function in a space of dimension 1, you know what it means. It's interesting. But what we saw is that in high dimension, samples are at equal distance from each other. So if you look at the distance matrix in a high dimensional sample, basically you have 0 on the diagonal and basically a constant value elsewhere. You have the same value elsewhere. And in this setting, saying that a function is smooth doesn't mean much. Because what you want to say is that a function is smooth if basically it takes similar values. You want to say that, for instance, the function is Lipschitz if x is close to y, then f of x should be close to f of y. But in high dimension, you only have two different values for the distance between two samples x and y. You have 0 if x is equal to x, and something like 1 if x is different to y. And so saying that a function is smooth, you're just saying that it's either constant or you say that it's bounded. But in high dimension, this constraint degenerates and becomes like a TV norm. So it stops being interesting. Okay? And that's exactly the same story for optimal transport, because optimal transport, basically it corresponds to optimization on sets of one Lipschitz functions or similar constraints. And likewise, saying that you are one Lipschitz when the matrix of distances between your samples just has two values doesn't say anything. Okay? A dual thing is to say, well, anyway, if I have images, taking the squared Euclidean norms between images is useless, more or less, except if you're working with MNIST. Remember that MNIST is completely toy problem. It's not representative of what real images look like. And so that's the situation where we were in. And then people starting to say, okay, maybe the fundamental insight of all this mathematics, of all this work in mathematics, is that we should constrain the set of dual functions. Smaller set of loss functions means more informative gradients. And so what people started to do with GANs is to say that we are going to solve this problem, but instead of using a mathematical class of functions, we're going to specify an architecture for our test functions. We're going to try to compute those kind of formulas when f is constrained to be a convolutional neural network with a given architecture. Okay? And this puts a very strong prior in the algorithm. Basically, you are constraining yourself to using perceptual test functions that care about texture. So this is what GANs are about. And it's a good idea, clearly, because it allows people to generate meaningful samples in high dimensions. But okay, unfortunately, the good thing about all those previous sets was that we had closed formulas for the loss. So we were minimizing a closed formula. With GANs, we are defining perceptual classes of functions. So we have to solve the min-max problem, and that's very hard. It's very complicated to do it. But okay, the point still stands that basically, we try to mitigate the curse of dimensionality by using perceptual sets of test functions. And that's the same story, okay, for diffusion models. I showed you that, okay, you have this picture that in the set of images, you have a data set of natural images, and we try to predict the gradients. So given any image, we try to predict a small vector field that takes us in the direction of the set of natural images. Well, if we're actually trying to solve this problem using arbitrary functions, it wouldn't work at all. Really, the secret sauce is that people use convolutional neural networks to solve this problem, to predict this gradient. And this is what makes it work. And visibly, I mean, you've all seen the images, I assume. It's really impressive. Okay. And so maybe the message to keep in mind from all of this is that this interplay, between mathematical insight that people have on toy models and numerical experiments on modern hardware is really what modern research in machine learning is all about. So that's why at the MVA we try to teach you both how to do good code and how to understand all this mathematical literature, because it's a very powerful way of getting new ideas of understanding what is happening. And so now, obviously, if you're at home, I advise you to try to play with gradient descent with all the loss functions that I showed you today. Basically, so you can find the links on my webpage. The workshops, you have an easy version, which is in the documentation of GeoMLOS, and then you have a much deeper version, which is hosted on my website with actual equations and all that, where basically what we do is we start from this kind of configuration, source point cloud, target point cloud. We define a loss function between those two distributions, like kernel, relative entropy, etc. And we try to see what happens when we minimize the loss function by gradient descent with respect to the positions of the samples. So it's kind of a toy generative model, and you learn a lot of things about the different loss functions by looking at the trajectories.